Hello, my name is Soufiane, and this is our work on weakly supervised object localization. So weakly supervised object localization are currently driven more by CAMs, which are easy to obtain. So you can train a classifier like this to using global annotation, for example, a class of the object, and you can obtain a localization using something like this, a rough localization of the objects. While CAMs are good, they have some drawbacks. For example, they can yield localization, blobby localization like this, inaccurate, that doesn't respect the boundary of the objects. And one of the reasons of this is the low resolution of the CAMs. So typically you can end up with a CAM that is 8 by 8, and then you need to interpolate to get back to the original size. And clearly here, the interpolation has less chance to cover exactly the objects because it doesn't look to the image when it does the interpolation. To show this, we take the true mask and then downscale by a factor, and then try to go back using interpolation to see if we can recover exactly the object. And when we vary the downscale factor, we see that it has major impacts on the accuracy, localization accuracy. So the higher downscale factor, the more error you would get in terms of localization. So to avoid this and avoid interpolation, we propose to use or to train to perform upscaling, parametric upscaling, where we train we use a decoder and train it using some priors to perform the upscaling to get something like this instead of doing interpolation. So to train this decoder, we use several priors. So we use the low resolution CAM to guide, to tell us where is approximately the objects, and also we use CF to align with the objects and respect the boundaries, and also prior about the size to cover the complete objects. So this is the architecture. We have here a pre-trained classifier that we use to get the CAMs, and we add simply a decoder here to yield the CAM foreground and background. And then here is the loss that the three terms of loss that I presented earlier. In terms of inference, we use the standard methods. Once we obtain the CAM, we use a typical procedure to yield the bounding box. So this is some results, visual results. As you can see, the CAM obtained by our method, respect the object, the boundary object, and covers the entire object. Another example here as well, another dataset, open images. We show as well that using simple baselines like CAM, by adding our method, we can push them to be state-of-the-art compared to other methods. So, and we tried this on several simple baselines. We also showed that our method is less sensitive to thresholding compared, for example, to other methods like CAM. For example, here, the more you vary it, when you vary the threshold, the performance, localization performance, varies largely. And our method, there is less variation. And we also look into the activation in the CAM. So, for example, here the activations are on standard CAM method. They are concentrated around 0, which is we expect actually 2 modes: foreground around 1 and background around 0. Our method starts to have those 2 modes, so it can separate properly foreground and background. There is also one drawback of our method. It's failed in some cases where the seeds are wrong, so we are feeding our method to wrong seeds, and this is actually an ongoing issue in learning. Because we are adding a decoder, so there are more parameters that we add, but when we measure the runtime, our method is actually competitive with other methods. Thank you. So please join us at the poster for more questions. You can find me or my supervisor, and this is our code. Thank you very much.